ഹലോ. നമ്മളിന്ന് സംസാരിച്ചത് സ്പെക്ട്രൽ ഷിഫ്റ്റിനെ കുറിച്ചാണ്. ഹൗ ദ സ്പെക്ട്രൽ മാക്സിമം ഷിഫ്റ്റ്സ് ടുവേർഡ്സ് either longer wavelength or shorter wavelength, or how the spectrum gains in intensity or gets a lower intensity. So all these effects are called bathochromic, hypsochromic, hyperchromic and hyperchromic effects respectively. So we are going to see a few effects that could lead to these spectral shifts. One of them is conjugation. Pi bond conjugation that facilitate the delocalization of pi electron density over more than one double bond or triple bond could shift the spectral absorption maximum towards longer wavelength or short lesser energy, and thus leading to a bathochromic shift. We are going to see this effect here. In the first case here, we have got only one pi bond here, so obviously there is just one pi molecular orbital and pi star antibonding molecular orbital, and both the pi electrons will be occupying the pi molecular orbital. And once this one of these pi electrons, when interacts with the radiation having a particular energy of 184 nanometer, one of the pi electron can get excited from the pi bonding molecular orbital towards pi star antibonding molecular orbital, leading to an absorption peak with a lambda max at 184 nanometer. And it has been observed that the approximate absorption coefficient or molar extinction coefficient for this transition is almost 10,000 moles per liter inverse centimeter inverse. But whereas if you consider a similar molecular system where both these hydrogens are being replaced to form a ethylenic double bond here, so that we have got two double bonds in the molecule but entirely separated by three intervening single bonds. So that these two double bonds, pi bonds, cannot interact with each other, and there cannot be any kind of pi bond delocalization in the molecular system. So for this molecule, the electronic absorption maximum is again observed at 185 nanometer, pretty close to the lambda max value for a molecule which has got only one single pi bond. So essentially this means that the pi bond transition energy remains the same irrespective of having two pi bonds in the molecular system now. But look at the molar extinction coefficient. This one gets doubled compared to the first case in here. So that means as the number of pi bonds which doesn't interact with each other increases in a molecular system, the molar extinction coefficient gets increased on an additive fashion. So or in other words, you can say the absorption intensity increases additively as the number of non-interacting pi bonds increases in a molecular system. So we can say that this one leads to a hyperchromic shift of the spectrum, but there is neither any kind of bathochromic shift or hypsochromic shift for the spectrum as long as we have more than one non-interacting pi bonds in the molecular system. But once you have two pi bonds which could interact with each other through an intervening single bond, or in a sense, or in other words, when we have a possibility of delocalization of pi bonds in a molecule, then the pi electrons can interact with each other, and this leads to a shift in the electronic absorption maximum towards longer wavelength. For this particular molecular system, lambda max is being observed at 217 nanometer. Compared to the case in here, you can see that the spectrum has got redshifter or the spectrum undergoes bathochromic shift. The molar extinction coefficient remains the same as the case here. So here again we have 2 pi bonds, here as well we have 2 pi bonds. So the molar extinction coefficient remains the same because in both the systems we have got only 1 pi electron in each double bond, which gets excited by absorbing 1 quantum of radiation. So the molar extinction coefficient remains the same. So you can see the same trend here. In this particular molecular system, this one is a general formula for a molecule where the molecule contains conjugated double bonds and represents the number of conjugated double bonds. So if n is equal to 2, we have got 2 interacting conjugated double bonds. So the spectra here represents n is equal to 3, n is equal to 4, n is equal to 5. So as you can see, as the number of n increases, the number of double bonds, pi bonds in the molecule that could interact with each other through delocalization increases. So you can see for n is equal to 3, this one is a green colored spectrum, is the electronic absorption spectrum, and which has got a maximum around 280 nanometer. Whereas for n is equal to 4, the electronic absorption spectrum has got a maximum around 310 nanometer. Whereas for n is equal to 5, the blue absorption spectrum shows an absorption maximum say around 350 nanometer. So you can see a clear trend here. The absorption maximum gets shifted towards longer wavelength, or it gets redshifted. Again, you can see one more trend here. On the y-axis we have got the absorption coefficient, and you can see for each 1 unit of the pi bond getting increased in the molecular system, the absorbance maximum or the molar extinction coefficient gets increased by a unit of 1. For example, compared to this spectrum is almost double the intensity, whereas compared to this spectrum is almost triple the intensity. So conjugation essentially plays a role in shifting the spectrum towards either red or blue region of the spectrum. The greater the conjugation, the greater would be the redshift. The lesser the conjugation, the lesser would be the redshift. So you can see that the first case here represents the ethylene system, which shows a pi to pi star transition at a wavelength of 175 nanometer, whereas the second molecular system here is the 1,3-butadiene system, which undergoes transition pi to pi star transition at 270 nanometer. And the third example here is the 135 hexatriene system, and which shows a pi to pi star transition at around 258 nanometer. So you can see the greater the conjugation, the greater is the redshift in the absorption maximum. You can also see that the molar extinction coefficient gradually increases upon increasing the conjugation of the molecular system. So finally, for beta carotene, we have got around 11 double bonds. You may count it to verify it. And for this particular system, the absorption maximum comes around 465 nanometer, with the molar extinction coefficient having a value of 125,000 moles per liter inverse centimeter inverse. So, and as another example, we have got a ketonic system here where the carbonyl functional group could undergo interpolar transition at 280 nanometer with a very feeble or very weak molar extinction coefficient, whereas the carbonyl system could undergo pi to pi star transition at around 189 nanometer with a molar extinction coefficient of 900, which is not very great but still decent compared to the molar extinction coefficient of n to pi star transition. But compare this case with the case of a dienone system, where an ethylene double bond is in conjugation with the pi bond electron density of the carbonyl system. Here you can see that the into Fieser transition energy is almost the same. It is unaltered, and the molar extinction coefficient is slightly off compared to the case here, but still it's very close. But you see, you compare the pi to Fieser transition energies compared to the case here for the first molecular system, which has got the absorption maximum at 189 nanometer. The conjugated diene shows an pi to Fieser transition at 230 nanometer, which is obviously redshifted compared to the unconjugated counterpart. And again, you can see compared to the molar extinction coefficient here, the molar extinction coefficient is at least 6 orders of magnitude greater than, or 6 folds of magnitude greater than the molar extinction coefficient here. So obviously conjugation shifts the spectrum towards red region, and also increases the molar extinction coefficient or the light absorption capability of a molecule. So for every observational phenomenon there should be a reason, right? So we're going to see why this conjugation shifts the absorption maximum or the transition energies towards the red region of the spectrum. So first of all, we are going to see the effect of conjugation on alkenes. For example, if you take, what is the simplest alkene system that you know of? So obviously ethylene or ethane, right? So we're going to see how the pi molecular orbitals forms in ethylene. In ethylene, the 2p orbitals, for example, you could take the 2p x orbitals, or say on the carbon. If you assume that the 2p orbital forms the carbon-carbon sigma bond, okay? So the 2p x orbitals on each of the carbons, for which you could assume that the wave functions are phi1 and phi2. So when they interact with each other, when they mix with each other, you know from Haeckel molecular orbital theory, they form a bonding molecular orbital having a wave function psi1, which is of character pi, because here for the 2p orbitals overlap in phase, okay, so that there are no knots, and the molecular orbital is antisymmetry with respect to reflection operation along the internuclear axis or rotation about the internuclear axis, and the outer phase overlap of these two wave functions, or mixing of these two wave functions, leads to an antibonding molecular orbital psi2 star, where the outer phase overlap leads to a node in between, okay? And obviously the electrons on both the carbons, the 2px electrons on both the carbons, occupies the lowest energy bonding molecular orbital psi1, and this is the energy gap, say for example between psi1 and psi2 star, okay? But what happens when you increase the conjugation of ethylene system? For example, you add one more double bond to the system to form, say for example 1,3-butadiene, okay? So we have dealt with the Haeckel molecular orbital theory of 1,3-butadiene as well, and there you know that the mixing of the 4 2px orbitals on the 4 carbons, when it happens in phase, that leads to a lowest energy pi bonding molecular orbital. Then the outer phase mixing of the orbitals on either side to the inversion center of 1,3-butadiene leads to another pi bonding molecular orbital, but which has got slightly higher energy than the lower pi bonding molecular orbital. Then when mixing occurs between two central 2px orbitals in phase, whereas on the 2px orbitals on the peripheral carbons are out of phase with the central 2p orbitals, then you have got two knots in the system forming a an antibonding pi star molecular orbital, and completely out of phase overlap of all the 2p orbitals on all the 4 carbons leads to 3 knots in between, and that leads to a pi star bonding molecular orbital having a wave function psi4 star. So these are the wave functions of the bonding molecular orbitals and the antibonding pi molecular orbitals in 1,3 butadiene. So from Haeckel molecular orbital theory, you should be able to tell that the 4 2px electrons on all the carbons, out of all these 4 2px electrons, 2 electrons will occupy the lowest pi bonding molecular orbital, whereas the rest of the 2 electrons occupy the next pi bonding molecular orbital psi 2. Okay, so this one is a HOMO, highest occupied molecular orbital here, and psi 3 star would be the LUMO, lowest unoccupied molecular orbital. So from Haeckel molecular orbital theory, if you calculate the energy difference between the HOMO and LUMO of ethylene and the energy difference between the HOMO and LUMO of 1,3 butadiene, you shall be able to see that the HOMO LUMO energy difference in 1,3 butadiene is considerably lower or lesser than the HOMO LUMO energy difference in ethylene. So that's the case. So and again, the electronic transition is nothing but the transition between the HOMO and LUMO of a molecular system. So you can see that compared to ethylene, the transition energy, pi to pi star transition energy, is much lesser in the case of 1,3 butadiene. So 1,3 butadiene is much little bit more conjugated compared to ethylene, and the transition pi to pi star transition energy is much lesser. So compared to the electronic absorption spectrum of ethylene, you should be able to see that the electronic absorption spectrum of 1,3 butadiene will be slightly red shifted. So this trend can be without solving the molecular orbitals of further conjugated systems. You shall be able to make a general concept that when you increase the number of conjugated double bonds in a molecular system, just like in the case of going from ethylene to butadiene to hexatriene to octatetrene, you shall be able to see that the number of molecular orbitals will be increasing with the number of carbon atoms in the system. Okay, and the HOMO-LUMO gap will be progressively getting reduced as the number of conjugated pi bonds increases. So in ethylene we have got only double bond. This is a HOMO-LUMO energy gap. In butadiene we have got 4 molecular orbitals and the HOMO-LUMO energy gap is lesser. In hexatriene again we have got 6 pi molecular orbitals because there are 6 carbon 2px orbitals involved in pi bond formation, but the HOMO-LUMO energy gap is again lesser compared to 1,3 butadiene. In octatetrene again we have got total 8 pi molecular orbitals because we have got 8 carbon 2px orbitals involved in pi bond formation, but you see the pi to pi star transition energy or HOMO-LUMO energy gap is much lesser compared to hexatriene, butadiene and ethylene. So progressively the HOMO-LUMO energy gap decreases. So as a hint, you can, if you consider that, if I give you a hint that if you consider that the structure of these molecular systems are almost linear, and if you just consider the energy of just one electron in these molecular systems, okay, so you may be able to assume that that particular pi electron, if it is free to move from one end of the molecule towards the other end of the molecule, then you may consider it as a particle in a one-dimensional system. So where the length of the box, one-dimensional box, is nothing but the length of the molecule. So you can see that when you go from ethylene to octatetrene, the length of the molecule increases and the length of the one-dimensional box again increases. So you have learned from quantum mechanics that the energy of the particle that moves along a one-dimensional box is nothing but n square h square by 8 ma square. So a is the box length. So from ethylene to octatetrene, the box length increases, therefore correspondingly the energy decreases. That's why we get a lesser transition energy for a much more conjugated system. You could also think about some sort of conjugation between an ethylene type double bond in alkenes and an oxochrome like a nitrogen, oxygen, sulfur, or halogens, nitrogen, oxygen, sulfur, and halogens. When they are being directly bound to the carbon which is involved in the ethylene double bond, then you may assume that the lone pair electron density on these oxochromes could just be able to, they could be able to interact with the ethylene pi bond electron density. So we have already discussed about such an example when we quoted benzene and aniline today morning. So the lone pair electron density on nitrogen in aniline should be able to interact with the pi bond electron density on benzene, and it could extend its conjugation. We have already discussed that matter in today's class. So if you consider such a simple case where an ethylene type double bond is being in direct bond with an oxochrome, we call the oxochrome A here, which bear a lone pair electron density. So in a sense, the lone pair can interact with the pi bond electron density here. Okay, so when that interaction happens, the electronic coupling between the non-bonding electron density and the pi bond density, pi electron density, would happen provided that the direction of the 2p orbitals involved in pi bond formation is almost, close to in plane orientation with the lone pair electron density. So the extent of interaction, electronic interaction between the lone pair electron density and the pi bond electron density would be greater if both the lone pair electron density and the pi bond, the 2px orbitals involved in pi bond formation lies in the same plane. Okay, so you can think about such an interaction, and you can think about the formation of molecular orbitals that could form out of this kind of interaction. So for such a simple ethylenic system, we can think about the pi molecular orbital and pi star molecular orbitals having energies right here, and the two electrons in the pi molecular orbital will occupy the pi bond will occupy the pi molecular orbital here, and then here we have got the non-bonding orbital on the oxochrome, which has got two electrons here. Okay, so once the pi bond or the pi star molecular, the pi molecular orbital, pi star molecular orbital of the pi bond interacts with the lone pair electron density here, it could lead to the formation of three molecular orbitals. The interaction between the pi molecular orbital of ethylene double bond with the non-bonding orbital will lead to a molecular orbital having a lower energy, which can be represented by the wave function psi1. Then correspondingly we shall be getting an anti-bonding orbital psi2 right here. Then the interaction between pi star molecular orbital of ethylene double bond with the non-bonding orbital will be completely repulsive, so we will get only an anti-bonding molecular orbital psi3 star. Okay, so we get only three orbitals. So obviously we have got two electrons here and two electrons here, and out of these four electrons, two electrons will occupy the psi1 molecular orbital and the other two electrons will occupy the psi2 molecular orbital. So think about the ethylene system. This one is a HOMO, pi is the HOMO and pi star is the LUMO. But see what happens when this one becomes in conjugation with the oxochrome. We have got three molecular orbitals, and here psi1 is not the HOMO, psi2 is the HOMO. Okay, and LUMO is the molecular orbital psi3 star. So if you compare the energy difference between the HOMO and LUMO of ethylene system, the energy difference between psi2 and psi3 star is lesser. So say for example, if we didn't have the oxochrome attached to ethylene system, we shall be seeing the electronic absorption at an energy corresponding to the energy difference between pi and pi star. But once the ethylene system interacts with the oxochrome, we have electronic transition from psi2 to psi3 star, which has got a lower transition energy, lesser transition energy, and therefore compared to the transition here, the spectrum that we get from the transition in here will be redshifted. Okay, so the oxochrome here redshifts the electronic absorption of the ethylene double bond towards a lower energy, or because of the oxochrome here, the absorption spectrum of the ethylene double bond gets shifted towards shorter wavelength. Okay, so this one is an effect of the conjugation between the non-bonding electron density on the oxochrome with the pi electron density of the ethylene double bond. Another type of conjugation that could happen is due to the interaction between the ethylene pi bond and the one of the sigma bonds in a methyl system which is attached to the carbon which is involved in double bond ethylene double bond formation. Okay, so this happens because of some sort of interaction called hyperconjugation or sigma bond resonance, which is better represented by this orbital picture here. So here we have got the carbon 2px orbitals which interacts in phase to form the pi bond in here. Okay, and here we have got the carbon 2px orbital on the methyl carbon which forms a sigma bond with the hydrogen 1s atomic orbital. So as long as this 2px orbitals, these 3 2px orbitals are in almost in the same plane, they should be able to interact with each other and they should be able to couple with each other electronically, and this effect is called hyperconjugation or sigma bond resonance. So this effect increases the conjugation of the pi electron density here, but not as much as to the extent of a real conjugation extension by adding pi bonds to the ethylene double bond system. Okay, so the effect is not much pronounced as in the case of pi bond extension. Okay, but still we see some redshift in the electronic absorption spectrum due to hyperconjugation or sigma bond resonance. Okay, so why do we study the effects that the oxochromes induce upon chromophores, so that we see an observable shift in the electronic absorption spectrum? Because organic molecules are nothing but molecular systems that are built up upon hydrocarbons systems with the functional groups attached to it. Okay, so the functional groups that gets attached to the organic molecular system could change the electronic absorption properties. So if you go in the other way around, if you could see an observable spectral shift in an electronic absorption spectrum, and if you could hypothesize as to why this shift happens, and if you could trace it back to the structure of the organic molecule, that could be a real advantage in organic spectroscopy. So there are some empirical observations of some non-conjugated structures that led to some empirical rules that enables us to predict the lambda max, that means the absorption max, electronic absorption maximum of molecules. And these empirical observations or empirical rules can be applied to unknown new molecular systems, so that we can use it to find out the molecular structure of the new molecular systems. So these empirical rules, there are two types of empirical rules. One is Woodward-Fieser rule and the other one is called Fieser-Kuhn rule. Okay, so we shall be first seeing Woodward-Fieser rule, which we apply to mostly 3 classes of molecular systems: conjugated dienes, then conjugated dienons, then aromatic systems. So in order to apply this empirical rule, we first consider, or we first take the one basic element of the molecular system as our base element. Okay, this basic element or base element has to be a conjugated system. Okay, but it should be the simplest conjugated system And for our information, one of the simplest complex conjugated system is nothing but 1,3-butadiene. So whenever we get a molecular system, and if we are asked to find out the absorption maximum, what we do is we first look for the presence of the 1,3-butadiene system in the molecule. Okay, that's our base element here. And 1,3, then what we do is we try to find out the electronic absorption maximum of 1,3-butadiene in the molecular system. Then what we do is we add up the empirical rules for any kind of substituents or functional groups that is being added to the 1,3-butadiene system in the molecule. Okay, I know this is confusing at the moment, but we shall get it sorted out very easily and clarified once we start dealing with doing some real problems, okay, which we shall be doing in the next class. So there are two conformers for 1,3-butadiene. One is the trans conformer and the other one is the cis. Okay, these two isomers are there. So essentially, compared to the trans conformer, which is the stablest form, the cis isomer has got a greater potential energy. As a result, what happens is the HOMO-LUMO energy gap of the cis isomer is lesser than the HOMO-LUMO energy gap of the trans isomer. Okay, these are the 4 molecular orbitals of trans isomer, and these are the 4 molecular orbitals of the cis isomer. So there can be 2 types of HOMO-LUMO transitions. One is the transition from site 2 to site 3 star, which happens at 270 nanometer for trans isomer, and the other one happens at 175 nanometer, which is forbidden for trans isomer, but which can be seen weakly for the cis isomer. And but this happens 175 nanometer is much lesser compared to the observation window of our electronic absorption equipments. We shall be seeing only the absorption spectrum corresponding to these 2 transitions, the transitions at 270 nanometer and 253 nanometer. So what we do is we try to locate or identify a trans isomer or a cis isomer in our molecular system, and then if we identify trans isomer, then we take a base value of 270 nanometer for the transition. Okay, or on the other hand, if we identify a cis isomer of 1,3-butadiene in the molecular system, we adopt a base value of 253 nanometer for our molecular system. Okay, so here you can see that the trans isomer has got a value of 270 nanometer and the cis isomer has got a value of 253 nanometer. So if we have got a methyl group attached to one of the carbons in trans isomer, you can see that the absorption maximum is slightly redshifted. Okay, so this is nothing but because of hyperconjugation. But if again when you have 2 methyl groups on either side of the trans isomer due to hyperconjugation, the spectral peak is again redshifted. Okay, if you have 2 methyl groups on the second and third carbons, we get the same value because of hyperconjugation effect. Look at the case here, benzene. Can you identify a trans isomer or a cis isomer in benzene? Okay, you let me know in the next class tomorrow, okay, whether you see a trans 1,3-butadiene or a cis 1,3-butadiene in benzene. Okay, benzene has got an absorption maximum at 256 nanometer. So here is an effect of extension of conjugation on 1,3-butadiene. If you take any the particular unit in here, from here to here, it is 1,3-butadiene, and this one is nothing but the conjugation is being extended by an extra double bond here. So you can see that compared to the lambda max of 1,3-butadiene, trans 1,3-butadiene, the lambda max of this molecular system is extended towards red region because of the extended conjugation here. Okay, so that's what we are going to try to do. So if you are given a molecule like this one, what you do is you try to identify whether you have got a trans isomer, trans 1,3-butadiene or a cis 1,3-butadiene in the molecular system. Then you add some empirical value to the original value 270 nanometer to get the experimental a value close to experimental value. Okay, that is the empirical rule. Okay, again, if you could identify whether we have got a trans or cis isomer in benzene, what you do is, then we have got an extension of conjugation here. You add a particular value to the original value of the parent 1,3-butadiene system to get the value, to get a lambda max close to 256 nanometer. Okay. Again, I know this is confusing right now, but once we start doing problems, you shall be able to see it through. Okay. So in Woodward-Fieser rule, if we have got an acyclic butadiene for dienes, and if it's a trans isomer, we take a base value of 270 nanometer. Okay. So what you do is, for every double bond that extends the conjugation of this 1,3-butadiene system, you add plus 30 nanometer to 270 nanometer. For example, if you have one more double bond here that extends conjugation, you add 30 to 270 nanometer. That could give you 247 nanometer as the lambda max of the new molecular system. Again, you have one more double bond that extends conjugation, then you have two double bonds that extends conjugation. Okay, then you add again one more 30. Okay, then if you could have something called extracyclic double bonds in a molecular system, which happens to be on the outside of a cyclic ring system, a double bond that's outside of a cyclic ring system. And you shall be seeing later what is an extracyclic double bond. Okay, for each extracyclic double bond, we add 5 nanometer to the base value. Okay, if you have an alkyl system substituted here, right here, or here, or here, or here, so for each alkyl system, we add 5 nanometer to the base value 270 nanometer. If you have an alkyl thiolate functional group attached to this system, then we add plus 30 nanometer. If you have halogens like chlorine or bromine attached to the 1,3-butadiene system, we add plus 5 nanometer. And if you have an amine substitute onto this 1,3-butadiene system, we add plus 60 nanometer. Okay, something like a tertiary amine. So this is the basic empirical rule for Woodward-Fieser type systems. Okay, so this Woodward-Fieser type systems means Woodward-Fieser type systems are systems that are acyclic or 6-member ring polyenes, and these rules agree very well for, works really well for acyclic and 6-member ring polyenes, but it does not hold good for other rings and the polyenes that are having more than 6 carbons in the system. Okay, again, steric strain is also another factor that could affect the lambda max value for an absorption band. Okay, sometimes the lambda max value could be shifted to a great extent if the steric strain is really high in the molecular system. Okay, for example, if you take cyclohexane having 2 methylene groups, 1,2-dimethylene cyclohexane, it has got a strong lambda max value, a strong band with a lambda max value 220 nanometer with a really decent or really high molar restriction coefficient. So a theoretical calculation of the lambda max values using Woodward-Fieser rule actually results in a lambda max value different from the observed lambda max value because of the steric strain between the two methylene groups on the cyclohexane ring system. Okay, so steric strain could lead to erroneous values if you use Woodward-Fieser rule. Again, Woodward-Fieser rule does not work really good for polyene systems having more than 6 carbons. Okay, so such polyene systems which have got more than 6 carbons, there is another set of empirical rules which is called Fieser-Kuhn rules. So according to Fieser-Kuhn rule, can be the Fieser-Kuhn rule can be embodied in some sort of equation. The lambda max value of a molecular system polyene in normal hexane can be represented by this particular equation 114 plus 5m, where m is the number of alkyl or alkyl like substituents on the conjugated system. We shall be seeing how to find out the number of alkyl or alkyl like substituents on the conjugated system, plus n is the number of conjugated double bonds, which is easy to find. We just count the number of conjugated double bonds in the polyene system into 48 minus 1.7 into n minus 16.5 into rn2. Rn is the number of rings with endocyclic double bonds in the conjugated system. So these are number of rings with double bonds inside, minus 10 Rxo. Rxo is the number of rings with exocyclic double bonds. Exocyclic double bonds are double bonds that appear outside the ring system. Okay, so we shall be seeing how to find out R endo and Rxo later. And the molarization coefficient can be approximated by 1.74 into 10 to the power 4 into n, where n is the number of conjugated double bonds. So we shall be using both the empirical rules for finding out the lambda max value of molecular systems later in this course. But for systems which are having a number of carbons less than 6 or equal to 6, we shall be using the Woodward-Fieser rule. Whereas for greater systems or lengthier conjugated systems, we shall be using the Fieser-Kuhn rule. And we shall be working out a few examples in the next class, and you shall be you'll be getting a grip of how to do these calculations using Woodward-Fieser rules and Fieser-Kuhn rule.